Hello everyone, welcome to this lecture series on diffusion models. So recently several generative models for images have come up, which include, for example, DALL-E or ImageGen. And basically these models, they take text as an input and you can generate fancy images based on the text prompt which you have given, text input which you have given. So one of the core algorithmic idea in these generative model for images includes the idea of diffusion models, right? And in this lecture series we are going to look at diffusion models in detail. Specifically we are going to look at the maths behind the diffusion models, right? And for coding part I'll refer you to other tutorials which are available online on GitHub or YouTube. This is the first part of the lecture series. Here we'll be reviewing evidence lower bound and variational autoencoders. This forms the crux for these diffusion models as well. So let's start by reviewing this. For some of you this might be the first exposure to VAEs also, so that's also perfectly fine. So let's first discuss what are exactly generative models. So essentially generative models, so what they do is that given samples xi, I from 1 to m, where each data point xi is sampled from a distribution px, a generative model learns to model this distribution as p theta x, right? So here we create some parameterized distribution and these thetas, they represent the parameters, and essentially the thing is that I want this p theta x to be somehow close to my original distribution px from which the data samples were provided. So now there are several approaches which people have tried for these sort of generative models. One of these, for example, includes GANs or generative adversarial networks. Another approach is that of variational autoencoders. So what GANs, for example, some of you might be knowing, what they do is that they have an like a discriminative part and a generative part. And essentially the thing is that the generator takes a noise as input, a random noise as input, and it tries to map it to the distribution of my desired data set. And the discriminator's job is to distinguish whether the sample came from my original data set or was it one of the generated samples, right? So here basically we have a sort of like an adversarial trade-off going on between this generator and the discriminator. We are not going to look at this sort of model today, whereas VAEs are essentially a variational autoencoder sort of family, and here essentially they model the distribution via a latent variable. So these are two very different approaches, and we are going to look at these VAEs first because essentially this is what leads us to the diffusion models, right? And first of all, you might be wondering, right, if we already had GANs, we already had VAEs, why did we need this sort of diffusion models, right? Because essentially there was a trade-off in the sense that GANs could produce good quality images, but training was hard in the sense that you could get stuck in one of these mode collapse problems. Whereas in VAEs, the training was slightly better, but the thing was that the quality of the images which you could get was not as good. So diffusion models somehow provide a trade-off between these two, and essentially they are able to produce good quality images without too much difficulty in training. However, the thing is that there is a lot of computational overhead which is associated with these VAEs. So with that, let's get started. And let's see what our algorithm is. So let's see firstly what's the algorithm behind VAE, and then we'll essentially look at the sort of the mathematical formulation and what cost function it represents. So even before looking at algorithm, one idea is that, in order to model this distribution Px, we are firstly parameterizing it as follows, that there is a sort of a latent variable which we are defining, z, and then conditioned on z, we have this data samples x. So we wanted to model the distribution of p theta x, but rather than modeling it directly, I model it through a latent variable, right? So there is a sort of a latent variable z, and what I do is that instead of defining the distribution of p theta x directly, what I do is that first I define a distribution of my z, which is typically some prior, it could be standard normal for example, and I define a parameterized distribution of x given z, the likelihood, and based on this I get the distribution of x as integral over z pz p theta x given z dz. Okay, so here the thing is that this is essentially an integral, and actually computing, like even if you have computed all these parameters and all, even computing this integral might be intractable. So the question is that how do we train it, right? And the algorithm which these VAEs define is as follows, is that you have this particular input x, right? So there is a sort of an encoder, you can think of it, and this encoder defines a distribution over my z, so some distribution. So this encoder has some parameter set phi, and it defines a distribution of q phi z given x. So for example, you can think of it, for example, like a feed forward network with a softmax layer at the end, and this helps me to define this distribution of q phi z given x. Or you can even think of it as, if z is, for example, continuous distribution, which probably people like that was the first way people could train a VAE. In that case, you can think of it q phi z given x as providing me a set of parameters for my Gaussian distribution. So this q phi z given x, for example, could give me the parameters of my distribution. These could be, for example, mean of z given x and covariance of z given x. Now given these, what I can do is that, given these parameters which are defining q phi z given x, I can try to get a sample of this random vector z, and this sample of this random vector z is then passed through a decoder. This decoder has its own set of parameters theta, and what it is doing is that it is defining the distribution of p theta x given z. Now overall, this helps me define, okay, so this is the overall network architecture, okay, and essentially what we need to train is to minimize the specific sort of objective function which is defined as follows. So this is the log likelihood of x given z. Okay, so there is a expectation over the sampled random variable z given x log p theta x given z, minus there is a KL divergence term, which is the KL divergence between q of z given x and pz. So here pz is my standard normal prior, for example, right? So there is a sort of a posterior distribution which this encoder is defining, and there is a sort of a prior, and there is a KL divergence term between these, and also there is this term of reconstruction loss, that from my z, what is the probability that I can recover back x. So this is the reconstruction term. This other term can be can be thought of as regularization term, right? Because essentially when you take two sort of normal distributions and say if they have the same covariance, then essentially this KL divergence turns out to be proportional to the square difference of the mean between them, right? So the difference of like basically the suppose if the mean of this distribution is mu1, this is mu2, then it will be like squared of mu2 minus mu1 squared. And if one of the means is 0, then it's essentially like sort of a L2 normalization, L2 regularization on the mean of q phi z given x, right? So this is like a regularization term. So what we are trying to do is that we want to be able to reconstruct the x back, but we don't want the parameters, this mu, to be to run too far away. So this is more like a regularization term. And you may think that, well, why do we have this KL divergence between prior and the trained sort of posterior, right? Why isn't it between posterior and posterior? So for that there is a reason, that because this objective function comes up from this mathematical framework of evidence lower bound, which I'm going to describe right now. Okay, and the thing is that one interesting algorithmic idea here is that we are sampling this Z. So how do we backprop through this sampling step? So that's a question, that how do you backprop through this sort of sampling step? So the idea over here is that what we are doing over here is that we are going to define this sort of variable Z prime as mu of Z given X plus sigma of Z given X. Okay, so we are going to define this Z as mu of Z given X plus sigma Z given X times Z prime, where Z prime is standard normal. So what we can do is that there is a sort of a random variable part, and there is a sort of parameterized part, and we are now splitting it across. So essentially there is mu and sigma which are coming from here. There is an external Z prime which is standard normal from here, and now I have split this noise part and the parameters part, and so the backprop only occurs through the parameterization part. The sampling part I have eliminated from my backpropagation path completely. So we look at all these things in detail. Let's first now let's take a step back and see where all this is coming from. So let's see how the formulation is. So the formulation is as follows, that there is some latent variable Z. This is distributed as a normal distribution. Okay, and then I have p theta of X given Z, and what I'm trying to maximize is this log likelihood of px, right, which happens to be log likelihood of integral over z pz p theta x given z dz. So I'm going to maximize over theta, this p theta x, log p theta x, which happens to be this thing, right? When I say I'm maximizing it across the sum over all data points. So the question is that how do we first even estimate it, right? So one thing you can do is that you can for example you can try to do sort of so this is an integral, and then you can express it as you can break up this integral into bins, and then you can sum over the bins, right? But the thing is that suppose if your Z is high dimensional, suppose if Z is, for example, say 100 dimensional, then essentially the number of bins which you will need, and essentially every dimension, if you split it into bins of size let's say for example 0.001, then essentially the number of bins which you will need is going to be exponential in the dimension, right? Because suppose if you have some box in the dimensions, right, and every dimension, okay, so let's say that this box has length L, and I break it into bins of size epsilon, and let's say it's a d-dimensional box, right? Then essentially the number of bins which get created, right, the number of these small cubes which get created will be of the order of L by epsilon to the power d. So essentially there are going to be an exponential number of these bins, okay, and the idea is that if I have sort of a large number of these bins which grow with d, then basically the integral will become intractable for large dimensional latent variable, right? And typically what we are seeing in this large deep learning sort of these domain is that our embedding sizes, latent variable dimensions are all growing larger and larger, right? So we are into the regime of billions, and now moving to the regime of trillions of parameters. So as the domain progresses, this is becoming even harder and harder, right? Even earlier, even for d equals 100, it will actually be intractable already. So essentially the thing is that we can't just sum it up, and even if what I could have done is that let me actually consider this integral of, let's look at it again, what the integral which we have, pz p theta x given z dz. Okay, so what I can say is that this is essentially expectation of z distributed from pz and then p theta x given z. So one way to estimate this integral is that I can take a sample of z and I can just compute p theta x given z, and this gives me an unbiased estimator of this integral, right? But the question is that what's the variance, right? And the variance is going to be high if you have like one sample, and again you'll need an exponential number of samples in order to bound the variance by some constant value. And the reason is again the same, and that as the dimension is growing, the variance of this quantity is also going to be larger. And the key reason is that if you have very few samples of z, it's unlikely that they'll be able to regenerate back x, right? So the thing is that because z is the sample from prior, and given an x, I may not get a good enough sample of z at all, right, if you're just sample from the prior. So the idea is that, well, can we sample z from posterior? So here the challenge is that firstly, how do I okay, so there are two challenges. So firstly, the first challenge is that how to get an unbiased estimator of log px from posterior. This is the first challenge. The second challenge is that that computing posterior distribution is also computationally hard, right? And the reason is that in order to compute posterior, we actually have to go back to computation of this marginal of px, and this marginal of px requires again an integral over z pz p theta x given z dz, right? So this integral itself was interactable, and that's what we were trying to compute. Now computation of this posterior again requires me to compute this thing. So exactly computing is hard, but the idea which solves both these problems, the challenge of computing the expectation carefully, as well as getting an unbiased estimator of this log px, as well as computing this posterior, this challenge is overcome if we use this idea of evidence lower bounds. Okay, and the idea behind this evidence lower bound is as follows, that okay, so the claim is that for any distribution qz, log px equals to expectation of log pxz by qz, okay, plus the KL divergence between qz and pz given x, right? And this quantity is actually something greater than equal to 0. So essentially what you can ensure is that this expectation is a lower bound for log px, right? And this is what is called as the evidence lower bound. Okay, so let's take one step at a time, and basically this lower bound is what we'll use in order to optimize log px. So let's take a step back and see where this is coming from. So essentially the thing is that I split this log px into two terms. The first term is ELBO and the second is a KL divergence term. The second term is always non-negative, which means that if I take it to the other side, this KL term, then basically what I'll get is that this ELBO is going to be less than equal to log px, because it will be log px minus some positive quantity, right? And in order to prove this claim, actually I would want you to pause this sort of video and try to prove this claim yourself. But yeah, what I can do is that I can try to give you some idea which is also short. So the idea is that so essentially if I look at the RHS, then essentially what I had was log px expectation over qz log px by qz plus the KL divergence between qz and pz given x. Okay, and essentially this KL divergence is also expectation over qz log of qz by pz given x, and overall I have an expectation over qz log pxz by qz times qz by pz given x, right? So which makes it expectation over qz log of right, so this is just px, and since there is no z inside expectation, I can just write it as log px, right? So this will hold true for any distribution qz, right? And from this quantity, since basically KL divergence is a positive term, what we get are these two corollaries. The first one is that expectation over q log pxz by qz is less than equal to log px. The second corollary is that for qz equals to pz given x, right, what we have is that ELBO, which was defined to be expectation over q log pxz by qz, this equals log px. Okay, so the first corollary we have already seen. This was true because KL divergence term is a non-negative term. The second corollary is true because if I set qz to be pz given x, then this KL divergence term will go off to 0, and once it goes off to 0, then log px and this ELBO, they will become equal. Okay. Now if I put these two corollaries together, what I get is this point 3, which says that max over all q expectation over q log pxz by qz, this equals log px. And the reason is that because in general what we have seen is that this ELBO is always less than equal to log likelihood, right? But for when qz and pz given x, they become equal, then ELBO equals log likelihood. So essentially if I maximize this ELBO over all possible distributions, what I'm going to get is that this equals the log px term. Okay. So essentially the idea in basically in this VAE is that if I now want to maximize log p theta x, what I can do is that I can maximize over theta, right, and maximize over all possible distributions q this ELBO, right, qz given x log pxz over qz, right. So thus in order to maximize with respect to q, we can we can choose q from all possible distributions, but since parameterizing all possible distributions is hard, what we do is that we choose q from a family of distributions which is parameterized by phi. Okay, so that is we choose the distributions from this Q phi z given x. Okay, and so this family of distributions comes from our neural network, which is the encoder. Okay, and overall this gives us two sort of parameters. One is the parameters theta, which are in this p theta x comma z, and the other is the parameters for my posterior Q phi z given x. So here we have two sets of parameters. One is the parameters for likelihood, which is theta. Here we have this p theta x given z, and others are the parameters for my posterior, which happen to be phi. These define my distribution Q phi z given x. And overall I need to maximize expectation of Q phi z given x log of p x z by qz. Okay, so here I can actually split this term into two parts. One is that Q phi z given x log p theta x given z, okay, minus the KL divergence between Q phi z given x and p of z. So this is called as the likelihood or the reconstruction term. So essentially what we are doing is that I have just split this ELBO into two parts. You can do it by rewriting numerator as x given z. Okay, so by writing numerator as pz times px given z, and then basically we'll get these two terms. So this is the likelihood or reconstruction term, and the other is the regularization term. And now if we take a look back at the algorithm, what we had was that we had the input x, we had this encoder with parameters phi. Right, this defines a distribution for me Q phi z given x. I produce a sample z and I send back this sample to decoder, and now I try to maximize the log likelihood of x given this particular sample z. And again, in order to backprop, we'll need to do this, perform the reparameterization trick. So essentially this forms the background of variational autoencoders. In the next lecture, what we'll try to do is that we'll try to define a sequence of latent variables, right, which basically gives us the hierarchical variational autoencoder models, and by then fixing the sort of form of the posterior, we'll arrive at variational diffusion models. In the third part, we'll look at the algorithm for variational diffusion models. Okay, thanks, bye.